For section 6, 2, 3, and 4, we are going to be using these starred sections in the book. So it's a second but equivalent method of teaching natural logs and exponentials. So let me first ask you to recall that when you write an exponential statement, y equal b to the x, b is the base, x is the input, y is the output, x is your exponent. That's equivalent to, double arrow means equivalent, to x is log base b of y. So this is a y equal f of x statement. And this one here is an x equals f inverse of y statement. And that was how we defined the inverse. So the inverse of a exponential base b is a log base b. For example, if you write 9 equals 3 squared, 9 is your y value, 3 is your base, and 2 is your exponent x. That's equivalent to 2 is the log base 3 of 9, 2 is your x, 3 is your base, and 9 is your y. So notice for the log function, y is the input and x is the output. So anytime you see a log statement like this, you can write the corresponding exponential statement to have it make sense. Now, I like to read this as 2 is the exponent over 3 that gives 9. And that helps you remember here that 9 is your input for this, 3 is your base, and then 2 is your x. So if you define logarithms in this manner, then log base b has the following properties. Log of x times y is log x plus log y. So that's saying that multiplication inside is equal to addition outside the log. Log of x divided by y is the difference of the logs, log x minus log y. The numerators first and denominator second. So division inside is equal to subtraction outside the log, top minus bottom. And then if you take the log base b of an exponential x to the r power, those inside exponents factor down. So that's r times the log base b of x. So inside exponents factor down. And then the log of 1 is always 0, no matter what the base is. And that's because if you write the corresponding exponential statement, b is your base, 0 is your input, 1 is your output. b to the 0 is always 1. So with this in mind, I wanted to find the natural log function here. So the natural log function, ln of x, is defined to be the integral from 1 to x of 1 over t dt. It's a definite integral, and that's for x greater than 0. Remember, this definite integral gives the area. So here's the picture of what's going on. Here is our y equal 1 over t. It's a function we're taking the integral of. And this case here is going to be if x is greater than 1, and over here if x is less than 1. Now x is always greater than 0. So really 0 less than x less than 1. So the natural log of x is going to be the area underneath 1 over t from 1 to x. So here's 1 right there, and then pick an x greater than 1 out here. So the logarithm is the area from 1 to x. It's that area right there. So that area is the natural log of x. So the natural log is an area function for 1 over t dt. Now what if your x is less than 1? So here's your 1. Here's an x value less than 1. And we find the area. In this case, the area is from x to 1 instead of 1 to x. X is less than 1. So x is smaller than 1. So if we do 1 to x, that is the negative of the definite integral from x to 1 of 1 over t. And this is smaller to larger here. This is area. So your natural log is the negative of area in this case. So ln of x is the negative of that area. So if x is less than 1, your log values are negative. If x is bigger than 1, your log values are positive. Now, notice that if we take the derivative with respect to x of the log function ln x, that's the derivative with respect to x of the integral 1 to x of 1 over t dt. Well, notice this is integral from 1 to a variable upper limit, and then we're taking a derivative. Well, this is just going to be the inside function. The integral and derivative are going to cancel each other out. That's fundamental theorem of calculus. It's the inside function 1 over t evaluated at the upper limit. It's 1 over x. And again, that's for x greater than 0. So that's fundamental theorem of calculus. So remember, fundamental theorem of calculus said this: if you take derivative with respect to x of the integral from 1 to x of f of t dt, you get f of x. So integral, derivative cancel each other out. You get the original function back at the upper limit of integration.